Today I'm going to give a fake proof of this limit, and I want to see if you can catch the first mistake. Okay, so my proof goes like this. If you want to prove that this limit is 0, well, we can rewrite this guy because sine n over n, that's the same as sine of n times 1 over n. So we can rewrite this as the limit as n approaches infinity of sine of n times 1 over n, since these guys are equal. And now by our limit laws, we can simplify, break this apart. We can go limit as n approaches infinity of sine of n times the limit as n approaches infinity of 1 over n. Okay. But now here's the thing, the limit as n approaches infinity of 1 over n, this is just 0. And so anything times 0 is got to be 0. So that proves that the limit of this guy is 0. So QED, baby. Okay, so let's see if you can find the problem with this proof. Pause the video if you need time to think about it. There's multiple things I don't like about this proof, but the biggest mistake is going from here to here without making sure these limits exist first, okay? Because this limit right here of sine of n, this limit actually does not exist, okay? And the rule which says that you're allowed to go from the product to this, it only works if the limits exist. There's a theorem that says if the sequence of ANs converges to A and BNs converges to B, then the product sequence converges to A times B. But notice the golden word here is if. So in order to use this theorem at all, you first have to prove that these guys do converge before you know whether or not this guy converges. Unfortunately, the way most schools usually teach this is by having the students memorize this as if it's some kind of magic formula. But the problem with this formula is that it's not always true. And so this is very dangerous. The safer way is to just forget about this and stick with the blue. If AN converges to A and BN converges to B, then the product converges to A times B. However, that's not the only thing that I don't like about this proof. Okay, and this part might be a little bit debatable, but I would argue that the first mistake is right here. Well, we're writing that this limit equals such and such, but how do we know this limit even exists in the first place? Because it's not obvious. It's something that we have to prove. But by writing this and doing manipulations with it, we're assuming the limit exists before we've even proved it. So I would argue that the very first mistake is right here. Okay, so now you may be wondering, well, how do you prove this for real? Let me walk you through the real proof. Prove this for real, we can take advantage of a theorem which says that if you have a sequence that's bounded and you have another sequence which converges to 0, then the sequence you get by multiplying them together also converges to 0. Okay, so in particular, we know that sine of n, well, sine is bounded between 1 and -1, right? So sine of n is a bounded sequence. And we also know that the sequence 1 over n, this converges to 0. So therefore, by this theorem, since we have a sequence which is bounded and a sequence which converges to 0, the sequence that we get by multiplying them together should also converge to 0. Okay, and now this guy's the same as, we can rewrite this as a fraction. This is the same as sine of n all over n. So there you go.